Geometry 11.2 Area of regular polygons. By the end of this lesson, you should know how to find the area of regular polygons. We've talked about the area of triangles and of quadrilaterals, but we really haven't talked about the area of regular polygons. And before we get started with too much of that, we need to think about a couple of different key pieces of regular polygons. Any regular polygon can be inscribed in a circle, and we call this circle the circumscribed circle. The center of this circumscribed circle is also the center of our regular polygon. And from this center, we're going to be drawing two special segments, one of which is the apothem. And the apothem is drawn from the center of the circle perpendicular to the side of our polygon. The other segment is the radius. This is the radius of the circumscribed circle, and the way you can tell that it's the radius when you're just looking at your polygon is it'll be drawn from the center of the circle to a vertex on your polygon. The radius and the apothem are both important pieces of our formulas that we're going to be learning today. Before we get to the area of regular polygons, let's derive how to find the area of an equilateral triangle. And some of you might be thinking, well, we already know the area of a triangle, which is 1/2 base times height. But if you're given a situation like this, where you are only given a side length, we're left stuck trying to figure out what the height is, because we're given the base, which we can say is S, but our height we don't know. And the height, remember, is going to be the altitude of this equilateral triangle. Since it's an equilateral triangle, we do know that it's equiangular, and each of its angles is 60 degrees. And when we draw in our altitude, it's going to create two special right triangles, meaning that we have two 30, 60, 90 triangles. This is helpful because from this, we should be able to figure out what our height is. So let's go ahead and draw in our table. Ooh, that's a 90. And our relationship for the side lengths, so A root 3, and 2A. And the only measure we really know is our side length, which we'll call S. And this might seem a little bit funny since we're working with all variables, but as long as you think back to what we did with our values, you should be able to come up with the height in terms of S. So before we would set whatever value we had equal to the relationship, so we can say that 2A is equal to S and solve for A. We'll find that A is equal to S over 2, which means that anywhere we see A in our chart, we can substitute in S over 2. Which means then, if the height of our triangle is the side length across from the 60-degree angle, our height is now known. And we can say that the height of this triangle is going to be S root 3 over 2. Since we have both our base and our height, we can substitute these values into our original area for a triangle formula. And we get area is equal to 1/2 our base being S and our height being side root 3 over 2. And we can simplify this to come up with a new area formula for just equilateral triangles using the side length. When we do this, we get side squared radical 3 over 4. Which brings us to our theorem, that the area of an equilateral triangle can be found by this formula that we just derived. So this is a nice way to find the area of an equilateral triangle when you're only given the side length. And let's try an example of this. So here we're given an equilateral triangle, and it says to find the area of the equilateral triangle. Well, now with our formula, area is equal to side squared radical 3 over 4. All we need is the length of the side, which we have. So we can substitute this value in, and we have 5 squared radical 3 over 4, which is 25 radical 3 over 4 units squared. Since this is our exact answer, and sometimes approximate answers are easier to use and more applicable in real life, we can go ahead and take the decimal answer for this, which is, oops, the following. Now we talked about the area of a regular triangle, but what about pentagons and hexagons and heptagons? Well, that's what we're going to come to next. And although we're not going to go through a formal way of deriving this formula, we can think about it and come up with it somewhat. So I'll guide you through this, and let's go ahead and create triangles in our regular polygon. And these triangles I'm forming by going through the center of the polygon in the center of our circle and drawing in the radius. And so from the center to each vertex, we've drawn the radius, and I've come up with 1, 2, 3, 4, 5, 6, 7, 8 triangles. You will always be able to draw as many triangles as you have sides. So whatever n is, that's how many triangles you'll be able to draw. Now, something that's important to know is that this angle that's formed is called your central angle. And this will be helpful in our formula. If I knew how to find the area of each one of these triangles, I can just multiply it by the number of sides and come up with the total area of our polygon. And we do have an area formula, which is 1/2 base times height. So the area of our polygon is the number of sides times each area of our triangle, which is 1/2 base times height. Now, even though we just derived a new area formula, that's only for equilateral triangles. And these triangles that are formed by the radii of our polygon might not always be equilateral. Now, something to point out here is that we came up with new terms for this, one of which is what is the base of these triangles is what we now call the side length of our regular polygon. So we can substitute that in place of b. The height of these triangles is what we called the apothem earlier. So we can substitute that in place of h. And this formula is the formula that you'll be using to find the area of regular polygons, which brings us to our next theorem. That the area of a regular polygon with side lengths s is half the product of the apothem a and the perimeter p. So we can say that it is 1/2 a times n times s. Or if you notice that the number of sides times the side length is just the same thing as the perimeter of the polygon, you can say this is 1/2 a times p. Let's try an example. So here it's asking us to find the area of the regular pentagon, given that the apothem is 12 inches long. So our formula is 1/2 a n s. Use this formula when you're given a setup like this, when you're given the apothem, because you will need to find some other measures. And it's easier to keep track of if you have it as the 1/2 a n s. Our apothem is given, and that's 12. The number of sides is 5 because this is a pentagon, which means we need to find our side length. Now, if we go ahead and draw in our radii like before, we might notice that we have a right triangle over here. And if I was able to find out this side length of our right triangle, I would be able to find out the side length of our pentagon, because the side length of our right triangle is half as much as our pentagon's side length. In order to do that, I would need to know an angle measure. And we just talked about how you can find out one of these central angle measures. So since all of these will add up to 360, we can divide that by the number of central angles we have, which is 5. So each of these central angles is 72 degrees. Now the central angle here is this entire angle. Our triangle is only, the angle that's part of our triangle is only half of that central angle, so that's 36 degrees. Now, as you can tell, these diagrams get a little bit messy, so it's nice to redraw them. So I need to solve for x. I know that this angle measures 36 degrees, and I'm given the apothem, which is 12. Looking at this, we will be using our trig from before in order to solve for x. So this is the angle measure we're working with. This is our hypotenuse. X is our opposite side, and 12 is our adjacent side. And we'll need to identify the trig function that uses the opposite and adjacent side. And that ratio is tangent. Tangent of theta is equal to opposite over adjacent. And then we can substitute the values we know. So tangent of 36 degrees is equal to x over 12. And as we solve for x, we get that x is equal to 12 tangent of 36. Now this x is this measure here. If I want to find out what my side length is, we already said that our side length is equal to 2 times x, which means the side length that we're looking to find will be equal to 24 tangent 36. This is your exact measure for the side length, and it's best to use or to calculate the area of your polygons with the exact measures up until the very end so you can have a more precise calculation. Now that we have our apothem, the number of sides and side length, we can substitute these into our area formula. So area is equal to 1/2, our apothem is 12, the number of sides is 5, and we just calculated our side length to be 24 tangent 36. Using our graphing calculator, we can get an approximation of what this is. So we have 1/2, which as a decimal is 0.5, times 12 times the number of sides, which is 5, times 24 tangent of 36. And we end up finding that the area of our pentagon is approximately 523.1 inches squared. Now this is a long problem, and it's going to be important that you organize your work, and we'll be practicing this a lot in the next couple of days. So now that we're finally done, it's time for a joke. And what did the clock do when it was hungry? Well, it went back 4 seconds.